Hello and welcome back, everyone. Moving on to section 5.4, calling this convergence tests for improper integrals. Let's remember all the way back to equilibria for dynamics. They were places, or really values, where the limit as time went to infinity of our solution to the dynamics was equal to some value, which we called the equilibrium value. But if we remember a little bit farther, a lot of times the solution to our dynamics, especially if it's an initial value problem, we're given by some integral from an initial time to the current time of another function, maybe of s, in the s variable. And if we're computing the limit as this time we're evaluating going out to infinity on the integral, that's really asking a question about an improper integral, or an improper integral of type 1 is how he's calling it. And so we were curious about when equilibria would exist by more or less computing the values of improper integrals. And if you can find the actual value, y(q), means that number one, the equilibrium exists, but number two, you've been able to establish what value it is. Sometimes we ran into integrals such as the one I've displayed in the middle here, e to the minus x squared over 2, where you can't actually solve the antiderivative in any sort of closed form, and yet if I went ahead and gave this some bounds, maybe 0 to infinity, this does equal the square root of pi over 2. We don't have the tools to establish that in this class, but maybe even without those tools, if we just wanted to establish that that integral actually existed without maybe necessarily being able to compute it, that's a valuable piece of information for anybody trying to predict the future, right? If we want to predict the future with dynamics and we say, yeah, an equilibrium exists, unfortunately I can't calculate it with my equations, that's an okay thing to come up with, because then you turn around and you say, fine, let's experimentally determine what we think it may be. And you perform a lot of measurements. Those measurements maybe are getting close to a specific value. And you can say, well, number one, the equilibrium exists. Number two, all of my measurements are getting close to a value. The equilibrium is probably the value that the measurements are giving me. On the other hand, even if the measurements were giving the same value over and over again, if the dynamics is showing that maybe an equilibrium doesn't exist, then you don't have nearly as much knowledge about the future. You could say, yeah, just because the measurements are giving a value over time that's unchanging, we don't actually know that it's always going to remain unchanging. Maybe our dynamics is predicting eventually it'll split away from this number that we see. So establishing the existence of an equilibrium is actually a very, very powerful tool. And so establishing the convergence and or divergence, it's important to know when something diverges as well, of an improper integral is very valuable, even if we might not know its value. Okay, we can worry about finding its value another time. That's not really the topic for today. You know, mathematicians are studying to this day better ways of finding values for integrals that are really hard to compute. So in calculus 2, we're going to be powerful enough in a lot of cases to discover the convergence or divergence properties of these integrals without necessarily forcing ourselves to be able to calculate them. And so let's start with what we're calling tests, right? Because in some sense we're testing whether or not one of these integrals converges. We're going to start with something called the p-test, which is actually a lot easier than you would expect any of these tests to be. This one we can actually calculate the value for these integrals, but it's kind of like the best test to refer everything back to when we're eventually going to look at more complicated integrals. And so the p-test, p by the way standing for power, the p-test is going to determine if the improper integral from some finite value out to infinity of 1 divided by x to the power p, and all of these functions basically look the same, right? They all kind of look like that. And if we're calculating the integral, then we're basically computing this area from some point x min on the left all the way out to infinity. So when is that area going to be finite? It's going to be finite specifically when p is greater than 1. Okay, that's when it's going to converge, or equivalently, you know, the area is finite. So you need p to be bigger than 1. So some examples of that would be like 1 to infinity of 1 over x squared dx, or 1 to infinity 1 over x to the 3/2 dx, right? Because 3/2 is still bigger than 1. So you're just looking for that power in the denominator to be some number that's strictly larger than 1. And we find out that in any other case, we have divergence. So diverges for any other case. You know, some common cases of divergence would be 1 to infinity 1 over x dx, or 1 to infinity 1 over the square root of x dx. Both of those cases are going to have infinite area. So that's a p-test, and this is the case when you have an improper integral of type 1, meaning the upper bound is infinite. I mean, the lower bound could also be infinite. The important thing is that we haven't divided by 0 within the range. If we look at the second statement in the p-test, here's that 0 in my lower bound. And now we kind of have to worry about, yeah, we're going to divide by 0 when we get close to that lower bound. What does the integral or the area that we're actually looking at look like in this second case? Now we're looking at the area that starts on the right, but actually starts moving up to the left and ends at 0. So it's that area we're going to look at now. When is that area infinite? It's infinite in the opposite setting. So it's going to be infinite when p is greater than 1. And so some examples of when the area is infinite would be like 0 to 1 of 1 over x squared, or 0 to 1 of 1 over x to the fifth. Those are both going to be infinite area, and we'll end up with finite area, so it converges in the opposite situations. So some of those would be like 1 over the square root of x from 0 to 1, for example, or even square root of x, right? Because that would be p is negative 1/2, since it starts at the denominator, the negative pushes it back to the numerator. So both of those would be finite area, which makes a lot of sense. Now, unfortunately, you would like to flip everything, but the special p equals 1 case is the case where no matter what, it diverges. Okay, so integral of 1 over x dx diverges at both 0 and infinity. It's not really a surprise, because what is that antiderivative? It's the natural log of the absolute value of x, and we know how the natural log behaves. The natural log is this function that kind of looks like this, right? And so it goes down to negative infinity near 0, and it goes out to positive infinity as we move to the right. So the natural log function gets in our way, and no matter what, if we're just doing 1 divided by x, we diverge. We can never have a finite area there. Now, why is this the nice one to refer to, this p-test? Well, you can actually just prove it. So we've got our proof here, which is, directly compute the antiderivative using the power rule and see what your limits do. And you're just going to see the answers that we have. Now, I don't really care about that proof. I care that you memorize the situations that are going on here. These p-tests are really invaluable. We try to compare almost everything back to a p-test, and otherwise maybe it'll be exponential, but exponentials are easier to deal with as well. So p-tests, very important. Try to memorize those. I gave some good examples. Let's go ahead and look at the next test. I haven't provided any specific examples of p-tests, since we can technically always compute them directly. This next test is kind of the first one that's going to be important for everyone, and we should talk about how the tests work before we get into this, right? So how do tests work? Well, they work in 2 steps. In step 1, you must show that a criteria of the test is true. This is always the tricky step. This is the one that students tend to like the least, is actually showing a criteria is true. And then in step 2, you use the truth of step 1 to make a valid claim. Right, a nice example of this, independent of p-test, would be, if it's raining, then I use an umbrella. Well, to know, not necessarily for it to be true, but to have knowledge, to have true knowledge of me using an umbrella. So to show that I am for certain using an umbrella, you must first verify that it is raining. Now, there are cases where maybe I'm using an umbrella and it's not raining. Those cases just aren't addressed by my specific statement, right? There's going to be cases, going back to improper integrals, where these integrals do converge, but the tests can only say so much. So even though you may want to claim it converges, you have to refer back to the test to actually produce the answer correctly. And so in our cases of raining, even though I may be using my umbrella for alternate means, if the only statement you have available to you is, if it's raining, then I use an umbrella, you must show me that it's raining first. I can't accept any other explanations about why I happen to have an umbrella if I'm only giving you the ability to use the statement, if it's raining, then I use an umbrella. So if you want me to be using an umbrella, you have to show me that it's raining. I won't accept anything else. Same things are going to happen in these improper integral tests, such as our first case here, the direct comparison, and later the limit comparison tests for improper integrals. So what's going to be the if it's raining, then I use an umbrella statement here for the, let's go with the direct comparison test first. The if it's raining part will be that we have to take 2 functions, 2 functions, and they must satisfy this criterion. So we need to establish that 2 functions satisfy this inequality. And we are curious about the convergence of one of them. Okay, in some cases you may be curious about the convergence of f, and that means you have the ability to choose g. In other cases, you may be interested in the convergence behavior of g, and that's going to give you the ability to choose f. But in both cases, you're going to be forced, once you make your choice on either f or g, and the other one's the one you're curious about, you're going to be forced to show that this is a true statement before you can move forward. There's a reason why we have if coming here, and then the true statement that you're forced to show. This is you forcing to show that it's raining before you decide to claim something with then. Once you've decided to claim something, you better show everything before it is true. But once it's true, you can claim that the integral of f is less than or equal the integral of g. Now that claim has very powerful consequences. Once we show our assumption that f is less than g, and they're both positive, then the claim that the integral of f is less than g has extremely powerful consequences, because if the integral of f happens to diverge, meaning it's infinity, then what can I say about the integral of g? Well, the integral of g has to be bigger than infinity. The moment I know the integral of g is bigger than infinity, well, there's only one thing bigger than, I guess, or equal to infinity, and that's going to be infinity as well. And so you can then claim not only that, the integrals are ordered as in the inequality itself, but you can claim that if f happens to be infinity, then g also happens to be infinity. You're going to be able to make a very similar claim in the case that g happens to be finite. Let's say it converges, because if I know that the integral of f happens to be smaller than something which is finite, then f would also have to converge. And so this is where the power of the comparison test comes into play. It lets you compare two functions as well as their two integrals together. Now you're going to have to make the choice on whether or not you want to test one function against something larger than it or against something smaller than it when you're actually dealing with these functions. And that's not always an easy thing to do. Before I talk about the limit comparison test, let's actually go into the example that I've provided of this direct comparison test. So we can try to compare the integral of 1 over x times 1 minus x to the 1/3 over the range 0 to 1. I want to compare it to something. But the real question is, do I want that second function to be larger or smaller? What's going to make more sense for me to compare this integral if I'm testing its convergence? Well, to really answer that, I need to know if I think it diverges or if I think it converges, and that's not always an easy thing to do. So that's actually my first job, is independent of comparisons. I need to decide, do I honestly think this converges or do I honestly think it diverges? And the reason why it could do either is because we are dividing by 0 at the lower bound, and in fact we're also dividing by 0 at the upper bounds. There are some divisions by 0 here. This certainly could diverge, but in some cases, like the integral of 1 over root x, by the p-test, we actually know that this converges. And so just because you divide by 0 doesn't necessarily mean you diverge. It means you have the chance to diverge. So we need to give ourselves some sort of guess as to whether or not we think this converges or diverges. Well, to do that, I'm just going to go ahead and compute the limits of this function near those 2 points of 0 and 1 and see what sort of behavior I have. So if I compute the limit near 0, I'm going to split my function at this multiplication of the denominator, and we call it 1 over x and 1 over 1 minus x to the 1/3, or individually, it's a limit as x goes to 0 of 1 over x and a limit as x goes to 0 of 1 over 1 minus x to the 1/3. Well, this second limit is easy to compute. Why is it easy to compute? Well, you just plug in 0. If I plug in 0 to that second limit, I just get a 1 out of it. And so everything here kind of reduces to, even though I've got the bigger limit right away, because I can plug in 0 to that second limit, it's really behaving like this, right? It behaves like 1 over x near x equals 0. So let's think about then, if I say it behaves like 1 over x near x equals 0, then this is really behaving like, or I'll say approximately like 0 to 1, 1 over x dx. But how does this function behave? The p-test, in this case, what is the power there? The power is 1, says diverges. And so now that I have some intuition that I think my integral diverges, I can actually start to decide how to use a comparison test. What sort of function should I compare to something I believe is diverging? Well, if I believe this is diverging, believe, but haven't proven this diverges, let's try to find something smaller than it which does diverge. right? If I can find an integral that's smaller than my integral, which also diverges, then it's going to force the integral I'm staring at to reach infinity. And so I'm going to look for a function smaller than this function. Look for a function smaller than this and try to show it diverges, the smaller one. Show that my smaller one diverges. In this case, I can basically only use the p-test. How am I going to try to find something smaller than 1 over x times 1 minus x to the 1/3? Well, let's just look at this term, 1 over 1 minus x to the 1/3. What do I know, at least within my range? What are my bounds on my original integral? They were 0 to 1. What do I know about those bounds? Well, as long as I plug 0 to 1 into 1 minus x, the value there is just going to be some number between 0 and 1. There's no way to achieve a different value if I'm only working in the range from 0 to 1. And so that denominator will be a number between 0 and 1, which means the entire term, 1 divided by the denominator, if I'm dividing by something between 0 and 1, 1 divided by that has to be something bigger than 1. Or if I get rid of my English there, what did I just say? At least in the range 0 to 1, which is where I'm integrating, what do I know? I know that 1 divided by 1 minus x to the 1/3 is strictly greater than 1. How does this help me? Because I wanted to find something smaller than my original integral. Well, if I flip this, I've just found that 1 is smaller than 1 divided by 1 minus x to 1/3. That's not exactly my original integral, right? My original integral had an extra term in the denominator. It had an x in the denominator there. How could I put an x in the denominator? Well, I could just go ahead and include an x in the denominator on the left-hand side. And now I've found something smaller than my original integrand. Moreover, this thing that I found that's smaller is exactly the intuition function that was telling me this diverged, right? Because I know that 1 over x diverges, at least within this range. And so what I've actually established is, number one, there is a smaller function, 1 over x, which is less than or equal to 1 over x times 1 minus x to the 1/3. And of course, these are both greater than or equal to 0. This is the equivalent of me showing it's raining. Well, now that I've shown it's raining, I can actually conclude, or in this case, that the one function is smaller than the other, I can conclude that the integral from 0 to 1 of 1 over x dx is less than or equal to the integral 0 to 1, 1 over x times 1 minus x to the 1/3 dx. That's me concluding I use an umbrella. But this conclusion has a very powerful outcome. That integral of 0 to 1 of 1 over x happens to be infinity, and so my extra integral is greater than or equal to infinity, hence diverges. So this is how we use the direct comparison test to show that an integral actually diverges. We have to establish that there's something smaller than it that also diverges first. Now that tends to be everyone's least favorite of the integral test. It tends to be the hardest because finding that function that's smaller than your divergent integral that also diverges is no easy task. You're really searching for a needle in an infinitely large haystack. I mean, there are infinitely many needles, but it's really not easy to find infinitely many needles in a much, much larger infinity of haystacks. So it's not an easy thing to do, and a lot of people hate it because of that. So what we have instead is actually this second comparison test called the limit comparison test, which tends to feel easier. It tends to feel more direct on how we may come up with a second function. And so with the limit comparison test, rather than trying to show that one function is truly less than or equal than another function, that direct comparison is a little hard. What we do with the limit comparison is we just go ahead and compute the limit of the ratio of two functions near the endpoints of the integral. Okay, there's me at x min, but you can also do this at the x max endpoint. And what needs to happen out of these limits of ratios of my two functions is I absolutely require a positive finite constant out of these ratios. Okay, a positive finite constant. That's now my equivalent of showing it's raining before I conclude this next step down here, which is that I use an umbrella. Okay, but what is the using the umbrella in the case of the limit comparison test? It says that if your f and g have this positive finite constant behavior at the endpoints, then actually the convergence or divergence of the integral of f happens to be equal to the convergence or divergence of the integral of g. And so you can directly compare the convergence or divergence behavior just by computing their limits at the endpoints. That's going to be the limit comparison test. I'll show you why it's a little easier to use in most situations. In our example does almost the same integrand. Notice I've flipped the denominator from 1 minus x to x minus 1. That's just to keep everything positive when I work over the range from 2 to infinity. We're going to try to show that this converges or diverges using limit comparison. Well, just as before, if I'm going to actually make a claim about convergence or divergence, I probably need some sort of intuition on whether or not this does converge or it does diverge. And here the intuition is going to be gained just by me looking at the two endpoints and computing the limits there. As I did before, if we compute our limit at this lower bound of 2, I can actually just evaluate a 2 in for both terms on x, and I just end up with a 1/2 there. So it ends up being continuous at the lower bound. We're not worried about divided by 0 or anything. It's really this upper bound. I'm curious, what is the behavior of this function near infinity, whatever near means, right? That's in quotes, unless we're compactifying the reals. Anyone who's taken like a real topology course may know what that means. But whatever near infinity actually means here, let's understand what we're trying to say. Well, if we decided to take a limit as x went to infinity of our integrand, what would it look like? Well, it would look like 1 over, let's plug a quote unquote infinity. We're going to be a little fast and loose with it today. Quote unquote infinity in for both copies of x. And well, the quote unquote infinity, if I subtract 1 from our super large number, it's basically going to behave just like that super large number again. Nothing's really changed. And so it's really behaving like that infinity to the 1/3 power. And then the infinity out front is infinity to the first power, or 3/3 equivalently. So 3/3 plus 1/3 is going to be 4/3. And so we can really say that, hey, this limit, when we're going all the way out to infinity, this is really me looking at like the highest powers. What does it behave like? It really behaves like 1 over x to the 4/3. It's more or less that negative 1's not playing any role when I push myself out to infinity. So let's think about the function 1 over x to the 4/3. How does that interact with the integral from 2 to infinity? Well, p, the power, is 4/3, and if I go back to my p-test page, that number is definitely bigger than 1, and as long as that upper bound's infinity, then the p-test says, hey, this converges by the p-test. And so we've got some sort of intuition that our original function converges, and now we can talk about why the limit comparison test works great. Once you have your intuition function, that intuition function almost always is the function we want to use for limit comparison. And so what's that going to look like here? Well, we're going to compare our original function 1 over x to the 4/3. And when we compare those two, we're going to hopefully see that the limit at the bounds is a positive finite constant. So let's go ahead and do that here. If I compare my original function to 1 over x to the 4/3, how do we work with the limit comparison test, right? We're supposed to compare, really at the bound that matters here, which is infinity, one function to the other using a ratio. And so I'm just going to plug in 1 over x to the 4/3 in the top. It doesn't matter which one you put in the top versus the bottom. I'm going to plug in 1 over x times x minus 1 to 1/3 in the bottom. And now I'm actually going to compute the limit here. How do I compute the limit? Well, I'm going to have to put a little bit of work in. This is a fraction divided by another fraction. And so what you end up getting is the denominator of the bottom fraction on top, and you get the denominator of the top fraction on the bottom. That's just algebra. And then we're going to simplify this a little bit, right? I can go ahead and rewrite this x as really what, x cubed to the 1/3, which means that, you know, both my powers here are 1/3, so I can pull that x cubed inside. I'm going to have x to the 4th minus x cubed. Similarly, in the denominator, x to the 4/3 is really x to the 4th to the 1/3. And so I've got a whole bunch of 1/3 powers here. I can pull the 1/3 power all the way out. I get x to the 4th minus x cubed over x to the 4th, or if I distribute my denominator to both terms in the numerator, 1 minus 1 over x. Very easy to take the limit of negative 1 over x as x goes to infinity. It's negative 1 over a very large number. It's going to be 0. And so you just end up that the limit here, the limit of the ratio of the functions is 1. And most importantly, 1 is a positive finite constant. That's what we absolutely require out of our limit of our ratio. Equivalently, this is me showing that it's raining. I can't make any conclusions until I show that it's raining. But once I've shown that this is a positive finite constant, now I can make the claim that the convergence behavior of 1 over x to the 4/3 implies the convergence behavior of the function that we actually care about. This is me using an umbrella. So once I've shown it's raining, I can claim that I use an umbrella. More importantly, the fact that this actually converges by the p-test means that I can actually claim that this also converges. But now I say this converges by the limit comparison test. So that's how I end up using a limit comparison test instead of a direct comparison test. We have 2 more tests that we're going to cover today. The next ones are a little bit easier actually and work with exponential functions more often than algebraic functions, right? The first 2 functions we analyze are algebraic. These next ones will probably work best with exponential functions. Let's look at the next one. It's called the ratio test for improper integrals. Ratio because, well, in the last case, limit comparison, I was computing a ratio, but I was comparing 2 functions together, f and g, using the limit of that ratio. In this case, the ratio test really refers to the fact that I'm comparing f to itself. So we compare f to not really itself, but kind of itself. You compare it to its derivative. Okay, so we're now going to compute the limit of the ratio of f's derivative to itself, and we're going to hope that out at infinity, this happens to equal some number L. Now, L could be a real number. It could also achieve, the values plus or minus infinity. We're going to treat those positive infinity as a positive number and negative infinity as a negative number. But if we can compute the limit of f prime divided by f, and we get some finite number out of that, and we ask the question, is that number positive, then we can actually say that the improper integral out at infinity diverges. If that number happened to be 0, then we unfortunately cannot use this test, so just forget about it. In other words, forget about the test and try something else. And in the case that we actually get a negative number, then we know that this integral converges. Really, when you work through the proof, which we won't here, but if you work through the proof, what you see is when L is greater than 0, then f behaves kind of like exponential growth. And of course, something that's exponentially growing should not have finite area out at infinity. You find out when it's negative, it behaves like exponential decay. And something which has exponential decay probably should have finite area out at infinity. So you find out when it's equal to 0, then you have neither growth nor decay, which is why this can't really tell you much. I mean, you may have growth and or decay, it's just not exponential. Exponential is a very strong version of growth or decay. So the 0 case we can't worry about. What would an example of using this ratio test look like? Well, we've got this case of e to the negative square root x squared minus 1. Now you can already see this looks like an exponential, but that square root x squared minus 1 is kind of getting in our way. How could we use the ratio test? Well, the ratio test says we need to compute the limit of f prime of x divided by f of x, so we're going to need to calculate f prime. Well, we calculate f prime just using a chain rule here, right? I guess the power rule as well. Chain rule is going to say we're going to keep the exponential the same, multiply by the derivative of the inside. What's the derivative of the square root of x squared plus 1? Well, we're going to get 1 divided by 2 times the square root of x squared plus 1. That's coming from the power rule using the power 1/2, which is the square root. And then you're going to have one more copy of the chain rule. That's going to be the derivative of x squared plus 1, which is 2x in this case. We decide to simplify this a little bit. We see we have negative x e to the negative root x squared plus 1, all divided by root x squared plus 1. Looks pretty ugly, but remember we're eventually going to be taking a ratio with the function itself. So if I take this and actually I divide the entire thing by the original function, what was that? It was e to the negative root x squared plus 1. Well, you actually see that there's an e to the negative root x squared plus 1 already up there. There's one over here in a denominator. They cancel each other. And so what I'm left with really is this negative x over root x squared plus 1. That's what I'm going to compute the limit of. That's what I ended up with over here. And now I compute that limit. How am I going to do it? The best way, easiest way, probably try to get rid of that x out of the numerator. You could use L'Hopital's. You're getting infinity over infinity, but I'm going to do it without L'Hopital's. I'm going to get that x out of the numerator by multiplying both the numerator and denominator by 1 over x. It's going to cancel in the numerator. I'm going to pull this 1 over x inside the square root. Well, to pull something inside the square root, I'm going to have to square it. So it's going to square through, and it's going to pull into the denominator of the denominator as an x squared in both cases. But of course, in the first case, x squared over x squared, those are going to cancel. Just going to have 1 out of that term and a 1 over x squared out of the other term. Well, what is the limit as x goes to infinity of 1 over x squared? It happens to be 0. So this ends up looking like the ratio of negative 1 over root 1, also known as negative 1. Now, what does the ratio test say I need my value to be? I need my value to either be positive, 0, or negative, and I really hope it's not 0 because the test doesn't do anything if it's 0. So I'm just asking questions about positive, negative, or 0 here. That number, negative 1, definitely is a negative number. And so the ratio test says, hey, negative numbers, exponential decay, this integral converges. And so quite easy, actually. Pretty nice. This is my version of showing it's raining. And it's pretty easy to say that I use an umbrella That's kind of a direct consequence of these ratio tests. It's very nice compared to our earlier tests. Our very last test for improper integral convergence is called the root test, and the root test is going to behave somewhat similar to the ratio test. It just gets calculated a little bit differently. We're now just going to take the limit as x goes to infinity of our function we care about, and we're going to take it to the power 1 over x. Why is this called the root test? Let's just recall that if I take a number, let's say a to the 1 divided by x, I can actually write that as the xth root of a. Xth is a really fun word to say. So it's the xth root of a. And that's why we call it a root test. But we're going to take that limit as x goes to infinity of this xth root. Now we're going to, once again, hopefully get some number out of this, but maybe that number could be infinite. But we're going to get a number out of it. If that number happens to be greater than 1, keep in mind the root test uses 1, not 0. The ratio test used 0. The root test uses 1. So we care about L being greater than 1. And greater than 1, it's still going to behave like exponential growth. Exponential growth is going to diverge. If it happens to be equal to 1, it's once again not going to behave like either exponential growth or decay, maybe some other version of growth or decay. So unfortunately, when it's equal to 1, you absolutely cannot use this test. Use a different test. And of course, your ratio test probably won't work in that case either. You'll probably get a 0 out of the ratio test. So I would use either the comparison or limit comparison test. And finally, if our value for L, this limit, happens to be less than 1, then we're going to behave like exponential decay, and exponential decay will converge. And so we're just going to test the values of L bigger than or less than 1 to see if our integral converges or diverges. Let's look at one lovely example here. This is the example I started today with. We technically know that this is equal to root pi over 2 if you've decided to memorize all the times I've said that. So we technically know that this converges, but let's actually verify that really quick. What do we have to do using the root test? We're going to grab that function. We're going to take it to the power 1 over x. The nice thing about taking an exponential to yet another power is that these powers just go ahead and multiply each other. When they multiply each other, what do we get? Well, we have an x squared divided by x. That's just going to give me a single copy of x in the numerator. But because I have a negative here, this is really e to the negative x or 1 over e to the x over 2. Either way you think about it, that's exponential decay. This function's decaying to 0. The limit happens to be 0. What does my test care about? My test cares about if that outcome is bigger than, equal to, or less than the number 1. How does 0 compare to the number 1? Well, 0 happens to be less than 1, so we converge. Once again, the fact that I'm showing everything actually is equal to 0 and less than 1. This is me showing it's raining, and then this is me concluding I am using an umbrella. So in all these cases, you have to show something before you can conclude something. And showing something will always be baked into the proposition you're using. Let's talk about some intuition before we finish off. So when should we choose any of our tests? Let's recall what we have. The p-test kind of plays its own role. This is only ever used for, like, algebraic reciprocals. Okay, so a very special class of functions. It's kind of the thing you refer back to when you're using comparison tests. But in terms of the rest of our tests, which are the ratio or root test, the limit comparison, and the direct comparison, the ratio and the root tests are basically behave the same in most cases. If you can use one, you can use the other, and vice versa. So you can't go wrong between the two of them, whichever one you choose. But when do you want to choose them? You want to choose them when the function is approximately exponential. Let's look at the cases we chose for, in this case, the root test. Look at that. That is an exponential function, or approximately exponential function. And similarly, in the ratio test, e to the negative root x squared plus 1, also approximately exponential. So you're looking at exponential functions for the ratio and the root test. Meanwhile, if you're going to use the comparison test, the limit comparison test is almost always a better choice than direct comparison. You're going to want to use the limit comparison for algebraic functions, and by this I mean powers of x, including square roots, including polynomials, rational functions, etc. And when we're going to compare these functions, I would almost always just do this highest powers trick, right? The highest powers dominate when functions behave a certain way. And so look at the highest powers, probably just combine all those together and use that function as your comparison function that you're going to compute the limit comparison with. So a good example of this would be something like 1 over x squared plus 1. You can compare to, well, what's the highest power is 1 over x squared. And 1 over x squared is really easy to work with because it's just a p-test function. And so that's when I would use the limit comparison. If everything else fails, you may periodically have to use the direct comparison test. A lot of times that's going to be the case when you have logarithms. So when you have a function that's clearly larger or smaller, which converges or diverges, more or less if you have a logarithm in your function, think about it as approximately equal to x to the point 0, 0, 0, dot, 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 repeating 0, 1 power. And then you can kind of use direct comparison and say that actually the logarithm is less than that power of x, and that'll get you where you need to go. That one can be the most tricky of all of them, for sure. So I would usually save that one to the last, try to use ratio of root when it's exponential, or limit comparison when it's algebraic. Anyway, that's all I've got. Pretty fun day, actually. I kind of like all these tests. Lots of talking about umbrellas and rain. Anyway, I hope the weather stays good for you. See you in the next one. Bye.